Hello chemistry champions, this is Werner. Welcome to the channel, or if you've been here previously, welcome back. In today's video, I'm going to show you how different isomers that have been experimentally prepared, isolated and determined for a triple bonded ditungsten complex. After that, I'll explain how each isomer was prepared. By the end of the video, you will see that inorganic chemistry, just like its organic counterpart, can have equally challenging problems when it comes to isomer detection and formation. Let's have a look.
In today's video, we are shown a tungsten complex that has a triple bond, two tungsten atoms, so it's a ditungsten complex, and each of the tungsten atoms has a chloride, amine, phosphine, and another chloride. So there's a total of three different donor atoms, chlorine, nitrogen, and phosphorus, and then there's obviously another chlorine on each of the tungstens, and the same on the other side. So what one has here, if one were to look at it from this side, is you would have a tungsten, and below it you would have a sort of square, and then each of the donor atoms, the chlorine, the nitrogen, the phosphorus, and the chlorine, will all coordinate. So if one expands this then to the other side, essentially what you have is a sort of cube. You can think of it as a cube. Like that. And in the middle of the cube you have two tungsten atoms. And so what happens is it projects to the side of the cube in each case. Chlorine, you can have a nitrogen, chlorine, and a phosphorus. So it means that each of the tungsten atoms here is now bound to these four donor atoms that sit on the face of one of the cube. If one looks at this one, the same applies. You can have a phosphorus, a chlorine, a nitrogen, and the chlorine. And so then this one will look like that. Remember that those two tungsten atoms sits right in the middle of the cube. So that is one way to look at it. So what essentially happens here is that if one can build little models, this is exactly what I'm trying to say. You have tungsten atoms sitting here in the middle of the cube. You have yellow chlorines, right? And you have red phosphorus, and you have blue nitrogen. And each tungsten will bind to two chlorines and one nitrogen and one phosphorus atom, donor atom. And so this can be considered a trans situation, because the chlorines are trans with respect to one another. So if you have the metal atom right in the middle, this will be a trans situation. Then another option is something like this, where you have the metal atoms in the middle. But now you can see that this situation is not the same as that one. In fact, this one now can be described as a cis isomer, because the two chlorines are on the same side with respect to metals that's right in the middle. So this situation is clearly different from that situation. And in fact, one can go one step further and say, if one is familiar with point group symmetries, this is a CI point group symmetry. The I means an inversion center, and that simply means right in the middle, everything that is on this side of the inversion center gets inverted to the other side. So this blue nitrogen atom gets inverted through the center, and it goes to the other side. Same with this phosphorus atom, inverted, goes to the other side. And then finally you have a situation where, now here, this one looks much like this one. You can say that this is also a cis isomer, but it's not the same. It's not the same as this one. This one, if one is interested in point group symmetries, can be described as a C2 symmetry, and that simply means that there's a 180-degree rotation axis that can be found. And so what that means is the rotation axis goes through the center here, and if one rotates it 90 degrees, 180 degrees, then you are back to where you started. So these are three different isomers that can be obtained from that particular tungsten compound. Let me know in the comments if you think there are other isomers available. The point is that these isomers have all been isolated, they've been synthesized, and they've been thoroughly characterized. So there's no question that they exist as shown here. So let's try to find out how they were made. So let's see how the authors went about making this particular compound. First of all, they had to start by making so-called starting materials, and the way they found to work the best was to work with tungsten hexachloride that they reacted with tungsten hexacarbonyl, and this was done in the presence of chlorobenzene as a solvent, and that produced tungsten tetrachloride. So the oxidation states here vary quite dramatically, because here you have a 6+ oxidation state, here you have 0, and here you have 4+. The next step in the process was to take the tungsten tetrachloride in THF solvent and a sodium mercury amalgam, and that created a compound that had 2 THFs associated with it, 3 chlorides per tungsten, and then the same on the other side. So now you see a situation where you went from a reduction of 4+ to basically 3+ for each of the tungsten. And also this clearly is a 5-coordinate tungsten compound, because the two of the THF coordinate to it like that. The next step in the process was to treat this compound with ethyl amine, and that is obviously the source of the nitrogen that we've talked about, and that was then simply treated with this compound. I'll just abbreviate it, WCl6THF4, and the authors then believe that this compound led to some intermediate So here you can see that one of the amines have been deprotonated compared to the 2 that you started with, and the other one has not yet. That seems to be in line with the final result. Then what happened was they treated this with the phosphine, trimethylphosphine in this case, and this was used in an excess. And the product that they formed then was the trans isomer that we've talked about, trans tungsten and the phosphines, two of those. And this process was followed with solution NMR, phosphorus NMR, and the peak for this phosphorus was found at negative 4.77 ppm. And then when this went on to stir further for about 15 minutes, then they started to see the other isomer start to form. And the first isomer that started to form was the Ci isomer that I've talked about. I'll just abbreviate it like this. Together with the trans isomer that was seen in solution. And this Ci had a phosphorus peak at 3.10 ppm. So clearly different from this one. Can clearly differentiate between these two. And then after about 30 minutes, the authors claim that they could see all three isomers, and the C2 has now started to develop. And after 500 minutes, they saw exclusively the C2. So it means that these products, well, this product most certainly was, let's say, a kinetic product, which then slowly over time transform into the more thermodynamic stable product. And this one had a phosphorus peak at negative 1.04. So clearly, based on the different peaks for the different isomers, the authors could conclude that they had different isomers in solution, and then they proved that by removing some of the solution and growing crystals from it, and so they obtained crystal structures for each one of the different isomers. So that was quite an interesting study, and it just goes to show that sometimes in inorganic chemistry one can have quite complicated isomer situations to deal with.
I hope you found the information on this isomer problem of value. Let me know in the comments how many isomers you thought this complex could have, if any, when you first saw it. Please also like the video and consider subscribing to the channel for similar content. Check out my other videos on the channel where we solve interesting chemistry problems. Stay curious, thanks for watching, and I hope to see you in the next video.